Hello everyone, welcome to this tutorial on takeoff, avionics of takeoff as explained in one of the very interesting patents from Boeing. The very focus of this patent is on the pitch of an aircraft, but if a person reads through this patent, he will get a very good understanding of the avionics and some other very interesting mechanism involved when an airplane takes off. So I will go through it if every aspect of this patent, and I will try to explain so that a very broad audience gets benefit from it. It's good for avionics people, aerodynamics people interested in aerodynamics, and just general people, general purpose tech interested people. So I would recommend you watch the whole video, and in case some portions you don't understand, I will request you to rewind it. Hopefully you will get the point, because I try to make it as simple but at the same time as comprehensive as possible for all of my audience. Also, one important thing I would like to mention, that this patent is particularly focused on Boeing 737-800 series aircraft. So one question comes, what about the 737 MAX or other types of aircraft like 777 or Airbus family? Well, a very common sense way of thinking is that if a person understands one aspect of one particular aircraft, the chances are high that in other aircrafts there will be some systems which will bear a lot of similarity with that. Of course, there will be some difference, but there will be a lot of similarity. So that's why in this in this video I will focus on one particular patent of Boeing, which is very focused on the Boeing 737-800 series aircraft. And after watching this video, the viewers can conclude and get a feeling and understanding of how this works inside. So also another very little bit different aspect I would like to comment on. This video is not at all related to the crashes which happened to Boeing 737 MAX series. Of course, I will give my own opinion. Maybe that opinion or judgment has some resemblance with what I discuss in this tutorial. Maybe it don't have some resemblance, maybe it's true, maybe it's not true, so that will be just an opinion. But with the understanding of this patent, you will get a lot of feeling of the takeoff mechanism. So let's get started with it. So here is the patent. So sorry, I have switched my screen to a pure patent. In here I have opened the patent. So this patent was filed in February 2018, and it was issued on May 28, 2019. So it's a very fairly new patent, as today is 1st of July as of making of this video. So the name of the patent is optimizing climb performance during takeoff using variable initial pitch angle target. So don't worry about the little bit complex topic. If you are not familiar with the term, we will learn all of it during the course of the tutorial. It was filed by these gentlemen, and the assignee is the Boeing company, and the owner of this patent is also the Boeing company. So let's get started with this patent. So first of all, to go for the understanding of this patent, we first need to understand this figure very carefully. Some of you people might understand it while other might not. So, but anyhow, I will go through it. So as one can see, this is the picture of a runway, right? This is a picture of a runway. Let me get the pen. Okay, so this is a picture of the runway, and here one can see that V1, VR, VLOF and VREF are written, right? So ignore the numbers like 22, 20, 26, 32, 28, 30, etc. Just consider these four uh, these four alphabets. So V1, what is V1? V1 stands for the speed at which the airplane can take off, right? So this is the speed at which there is sufficient flow of air over the wings of an aircraft that aircraft can get airborne. So this is the V1 speed, right? You might have heard when the pilots are taking off, this there's a automatic call, say V1, and then they say rotate. So this is the V1 speed, right? And just as I said, rotate. So a few seconds later, 4 seconds later, this speeds come into picture, which is the rotate speed, right? So first comes V1, then comes VR, right? You might have heard this speed in a lot of occasions. And then there is a third speed called V liftoff, right? So V liftoff comes immediately after VR, and this means that the plane the nose gear has lift off the ground, right? It is just about time that the whole airplane takes off from the ground, right? And the speed at which the whole airplane is up in the ground and it is 35 feet above the ground is called V2, right? It is here written. So V1, VR, V liftoff, and V2. So V2 is also called the safety speed, and this V2 will be used in the rest of the tutorial, along with another speed which is called VS, right? VS. So VS is not mentioned here, but it's mentioned in the figure, but it's mentioned in the tutorial. So VS is the stall speed. We have to understand what exactly is the stall speed in case you are not familiar with it. So stall is the condition in which the airplane is not flying properly, or the airflow over the wings of the airplane is not in a proper manner, so that the airplane is falling from the sky. This is the stall speed, and it's a very dangerous speed, and and a properly flying airplane has to operate above the stall speed at every circumstances, right? Otherwise it will get destroyed, it will hit the ground. So how much the normal operating speed or the cruise speed of an airplane should be different from the stall speed, there's another topic of discussion, and why some airplanes have different stall speed, that's a totally different topic. But you have to think in mind that V2 should always be greater than V stall, right? You have to think this way, right? This is for the proper operation of an aircraft, right? What does it mean? If V2 is greater than Vs, then it clearly means that the ratio between V2 over Vs will always be, and it should be greater than 1, right? So just keep this fact in mind, that V2 or Vs ratio should be greater than 1, right? So far what we have studied is the V1 speed, VR speed, V liftoff speed, V2 speed, and then I talked about the Vs, which is the V stall speed, and then I said that the ratio between V2 over Vs should be greater than 1, because this will be used in the later section of this tutorial when we would be talking about this pattern. Another small thing which I have to talk about is what is the pitch of an airplane, in case you don't know. And the pitch of an airplane is the angle. What is the angle which an airplane makes with respect to the ground? With respect to the ground. So if the airplane is oriented like this, somehow like this, so this angle which it makes with the ground is called the pitch. So how much the nose is up with respect to the ground is the pitch of an aircraft. So you have to understand, the higher the pitch, the more energy, or the engine has to provide a lot of power to overcome the drag so as this fly. For example, if the airplane pitch is like this, so to maintain the lift, to have a proper aerodynamic flow, it has to sustain, it has to have a lot of energy to fly in the high pitch. Conversely, if the pitch is directed downwards, or then of course the airplane is headed towards the ground. In rockets, for example, it's really vertical, so it needs a huge amount of energy to lift off and to overcome the forces of gravity. In any case, this is the pitch of an aircraft. So you have to understand what pitch means, right? And pitch is different than the angle of an attack. There is some people confuse angle of an attack with the pitch of an aircraft, but just to make sure, angle of attack simply means the angle at which the wings makes with the with the horizon. So again, that's maybe a different topic of discussion, but we are talking here about the pitch, which is just the angle which the nose makes with the aircraft, right? So now we will talk about two very important definitions which will be used in the forthcoming figures which I will be discussing. And those two definitions are, the first is the climb limit and the other is the field limit. So first of all, we need to understand what does field limit means. That's so you all would agree that the runway has a finite length, right? The runway is not an infinite piece of land available. So as for any aircraft, it is limited on the horizontal axis due to a finite length of the runway. So this limitation is called the field limit, right? It means that for any aircraft in the world, it cannot run on forever on the runway to take off or something. The runway has to have a horizontal ending, and this limitation is called field, and it's a very simple thing to understand and follow. The second thing is, of course, one is along the x-axis, the other limitation is along the y-axis for obvious reason, and this is called climb limit, right? So this means that the airplane has to climb or clear certain altitude when it takes off, and there are regulations and rules for this. So one simple rule is that at V2 speed it has to be above 35 feet above the ground, right? So the second limit is called the climb limit, and these limits are very important when it comes to in designing the avionics, when it comes to the takeoff of an aircraft, and this we will see now in the coming important diagrams which are implemented inside the avionics of aircraft, right? First of all, we will go to those important, very interesting figures which are easy to follow, and they give us very deep insight into how they are implemented inside a Boeing 737-800 series aircraft. So first of all is this figure. So we have discussed all the definitions earlier. In case you have missed it, you can relook it again at the beginning of the video. So here is the diagram on which on the x-axis we have V2 over VS, right? So it's the safety takeoff speed versus the stall speed, right? And on the y-axis we have the weight of an aircraft, the complete weight with all the cargo and everything. So, and here we can see that there is a optimum for a optimum V2 over VS ratio. There is an optimum point which with which the aircraft can carry maximum climb weight, right? So you have to remember this point, that this diagram is not like a sort of a linear diagram or sort of an exponential diagram like this. It is sort of an inverted parabola, right? You have to keep this thing in mind. It's an inverted parabolic diagram. So it has the two limits on the lower side of the speed V2 over S ratio and the higher side of the V2 over S ratio. I would say you just convince yourself here that the optimum point lies in the middle. It's not on the either ends of this graph, right? But just for understanding, we can think of it like this, that if an aircraft achieves if an aircraft has a very very high V2 over VS ratio, right, it means that it has a very high takeoff speed, then it certainly means that it has to have retracted flaps so that it is able to take off at very high speed. But again, this will not be possible because the aircraft will reach its climb limit. It means that it won't be able to take off with the high with the maximum available climb weight, right? So it has to have reduced climb weight in this regard. And also again, this will be limited by a climb limit. It means that it won't be able to sufficiently go out sufficiently attain enough height from the ground, right? So aircraft is limited on the horizontal on this graph along the x-axis by on one side on the climb limit, and here it is limited again by the fact that for a very low V2 or VS speed, an aircraft cannot have very high maximum climb weight. One easy way of understanding this is one analogy I can give, and you just convince yourself about this. Suppose there is a hill out here, right? and a person wants to climb that hill. So he cannot move and he has a certain weight on his back, right? So that person cannot move very slow, right? He cannot move very slow, he will roll down the hill. Secondly, if he moves very fast to climb the top of the hill, he will not be able to carry a lot of weight, he will get tired, and he will need very high amount of energy, right? You can think of it this way. So there is a point in the middle, depending upon the weight of the weight he is carrying, with which there will be a certain speed, so he will climb the top of the hill. So this is the same for an aircraft, because at very high speed it is also limited by the friction and by the engine powers as well. So the optimum point for V2 or Vs ratio versus the weight when it comes to maximum climb weight is in this middle point, right? So just keep this graph in mind, and now we will go to the next important graph, which is figure number 6. So we talked about limitation due to climb limit. So this is a very similar graph, but here the limitation is due to field limit, right? Due to field limit. So here you can think of it this way: if the aircraft want to have very high takeoff speed, right, again it won't be able to take a lot of weight. We saw it in the previous graph, right? Just to we can see it that with very high V2 or Vs speed, it cannot take a lot of weight. We can see here very easily. And now if we want to have a situation where aircraft has to have a very high speed, what is the limitation of the field? So it will get field limited. It means it will need a very long runway to cover, right? It will need a very long runway to cover, and it won't be able to take a lot of weight with it as well. Again, here it's also a very common sense thing that with you can take a lot of weight, a lot of takeoff weight if you are slow, right? So that's why this graph is like a decreasing exponential characteristics, right? So you have to convince yourself on those graphs that one is the decreasing exponential characteristics, right, like this, and the other graph is a parabolic shape, which is this one, right? In inverted parabola, you can call it, if I'm not wrong. So we talk about these two graphs. Now very obviously aircraft has to have a certain field limit and certain climb limit, right? So what we do is we combine the above two graphs. Very simple. So this is the graph of the field limit, the parabolic shape, and the decreasing exponential shape, and this is the graph of the climb limit, which is the inverted parabolic shape, right? So when these two graphs are combined, we have this sort of curves with us, and the intersection of these curves gives us the optimum V2 over Vs and the optimum weight. That you should convince yourself on it. It's very obvious that there will be an optimum meeting point of these two characteristic curves, one curve for the field limit, other for the climb limit, and this intersection point determines the optimum weight for which there is an optimum V2 over Vs ratio, right? I hope it's clear. It's quite straightforward, right? So now we will continue with those graphs, and then we come with another type of graph, which again, for obvious reason, we will combine it in the end. So this is the graph of V2 over Vs ratio with the pitch angle, right? So it has a characteristic, you can call it a sort of a linearly increasing characteristics, then it sort of reaches the peak, a sort of a compression, and then it starts decreasing. So it's a linearly increasing and then compressive characteristics, right? So here the thing is that the optimum point, the optimum pitch angle for a certain V2 over Vs ratio lies somewhere around here. It's not here. It is due to aerodynamic characteristics, the aerodynamic drag, and all other factors involved, that this point lies at the beyond the compressive characteristics somewhere here, right? So here they have said that for 1.3 pitch 1.3 V2 or Vs speed, the pitch angle is around 14 degrees, right? Of course here the pitch angle will be very high, the aircraft will be like very steep rising position, right? So it's not very high, it's not very low. Here it's very low sort of pitch angle, something like this. Here is quite optimum, right? You can think of it at this way. So this was our third graph, right? So now what we do is we will start combining one graph after we will start sort of combining those graphs and try to see them in a big in a big picture, as to say, right? So this is the graph again of v2 over vs versus the takeoff weight of an aircraft, and we are plotting against field limit for different pitch angles. This means that when the aircraft is limited by a certain field limit, certain runway, available runway with different pitch angles, right? We talked about a pitch angle just before. For different pitch angles, what are the characteristics of weight versus V2 over Vs ratio, right? So here we can see that there is a certain pitch angle phi 3 for which at low speed the aircraft can take a lot of weight, right? Or aircraft can take a lot of weight, but at the higher end it is not able to take a lot of weight, right? It goes steeply down. If one point is here of this curve, the other point is here, and the middle point is somewhere here, right? Similarly, for a very low pitch angle at low speed, it is able to take higher amount of weight at high V2 or Vs ratio, but similarly in the intermediate point it's lower than the other pitch angle. So what we can see is there is a wide range of characteristic curves for certain pitch angles versus speed limit in the context of weight versus V2 or Vs ratio, right? So maybe if we have another phi 0, let's say, it might have characteristics something like this, right? It's something like this. It's just my there are different characteristics based on those parameters. So we are trying to combine all those parameters together, right, to give us a big picture, right? And now we will come to a limiting case, right? The aircraft cannot have arbitrary values of pitch angle and anything. They are of course limited by the characteristics of the aircraft, the friction and all the other available features it have. So we will now reach the limiting case. What's the limiting case? That will be indicated by the next figure. Right. So here in the next figure, as we see, it is just the extension of the previous graph, right? It's a previous graph, but in the limiting case. We have to remember it. It's a previous graph in the limiting case. As I said earlier, there are just available set of pitch angles, right? Maybe there is one pitch angle here. Its graph goes something. Its graph goes something like this, but this is maybe not feasible. This is not feasible. The aircraft will just crash, right? Or it might need a very, very high field limit, or so this is not possible. Just think it this way. So it means that all these graphs are limited here, right? There's a limitation here. This is limitation, right? So this limitation is called optimum pitch target law, right? That these curves should not cross this this point beyond, and this is a very optimum point as well, right? So this is a optimum, this is called optimum pitch target law line, you can call it this way, right? I hope you are following it. It's very interesting but pretty simple stuff going on here. I hope you are getting, right? So now what happened is, now we are combining the ultimate thing. We are combining what we are doing. We are combining the V2 over Vs versus weight, and we are plotting this against that optimum pitch target law, because now this includes the pitch as well. Remember, in the previous graph of similar sort, we did not include the pitch. You remember it, right? Here we are including the pitch. So this graph gives us a very optimum V2 over Vs ratio versus takeoff limit, right? Which is some point here, right? I hope you are following this. So that's all. These are the very important graphs, and now we will in the coming section we will talk about how these graphs are incorporated inside the avionics of a 737-800 and similar maybe aircraft, to give to understand how the takeoff works at the avionics level. So now we have reached the final part of our presentation, which is the implementation of the previous discussion inside the avionics of an aircraft. So in this case, a 737-800 series or similar type of aircrafts. So first of all, we will talk about the complete flight control system, and then I will show you the algorithm and the more details of the system. So first of all, consider this figure. Maybe you are aware of it, or maybe in case you're not much into avionics, it might be a little bit tricky to understand, but it's a very compact figure. So you have this box as indicated by 2, which is the flight control system, right? So this is the flight control system box. So this is the brain of the aircraft, as to say, right? So what it is doing, it is getting a data from ADIRS, which I will explain in a minute. ADIRS, and then it is giving commands to the actuator, which then in turns drives the flaps during the takeoff. And also it generates the initial, it displays the initial pitch target on the display computer, right? It's pretty interesting. It's pretty straightforward, right? So first of all, we will look at what is ADIRS. So ADIRS is a whole bunch of sensors which senses the data from the outside environment, which senses the outside environment and gives the data to the input signal management platform, which processes this data, right? So what's inside the ADIRS? So ADIRS stands for, as we speak, for initial it's air data and initial reference system, ADIRS. So it is getting air data and inertial reference data, right? So it is composed of the air data. It has 2 parts, like, which is air data part and the initial reference part. Air data part gives the airspeed, angle of attack, temperature, and the altitude data, while the initial reference part gives the altitude, flight path vector, ground speed, and positional data, right? Due to the sensors of angle of attack sensors and other sensors, which are mostly in front of the aircraft, as we say. So this whole bunch of data is gathered, right? So again, I come to the back to the same picture. So this whole bunch of data is gathered, and it is input to this input signal management platform. This is also a computer which processes, it's a microprocessor which processes the data, and along with that, autopilot and the primary flight control. Primary flight control is what pilot gives the input, right? And the autopilot is the complex algorithms which automatically determines different parameters for the aircraft, right? So and also this flight management computer. So all of these combine. Again, this can be a long discussion how the inside of each and every block here looks like, but that's not the point here. The point here is that ADIRS data is it is processed inside here, right? And then based on this data, it generates the command to the actuators, right? Actuators are the moving parts, which are the motors. The signal is given to them, and then they actuate the flap setting, right? Based on the calculation on the weight of the aircraft and the other factors, which we will see in a second, which we'll see in some time in a formula, which is a very complicated mathematical formula which indicates how many parameters are involved here, right? And also it also based on this data, it generates what should be the ideal pitch angle, and this is also displayed here. I hope you are following this. So in this way, the initial pitch angle is calculated. Again, there are some other aspects. We just look at it one by one here, right? To avoid any sort of confusion, please hold on a second. Yes, so this is if a person wants to go inside the theory and how much dependence the pitch angle has on different factors. So this is the mathematical equations out there, right? So it's pretty complicated. It's not as straightforward as one thinks, but it gives a very interesting insight into the lot of interdependency of factors, that how the pitch angle is calculated, right? So in this formula, the pitch angle is like wait, I just zoom in. So in this formula, the pitch angle is dependent upon pitch angle phi is equal to a naught plus f naught plus rho 1.225.5. It's pretty long, right? So this is a naught is the angle of attack, right? Angle of attack. F naught is the takeoff thrust in newtons. Of course it depends how much is the pitch angle, also is a strong factor of the thrust generated by the aircraft. Then you have and it is also of course calculated by the flight management computer. And then you have the bleed and anti-ice status, the temperature. CDO is the drag coefficient, which is a factor here, and this again C1 is here, right? So inside this formula, these terms itself are big formulas in its own right. C1 is dependent on this, C2 is dependent upon this, V op 2 is this formula dependent on this, and the rho which is here is this. So every term in this calculation itself is a big formula in its own right. So you can see the complexity of this equation. So as we are speaking, so CDU, which is a parameter here, is a drag coefficient. S is the airplane wing reference, which is here, right? And then the other parts, you don't need to understand whole what it means, but just the point is to get the feeling of it. The main is to get the feeling of it. And then the other parts are of this formula, CL max, right? CL max, and E is the span efficiency, also known as the Oswald number. AR is the wing aspect ratio, and so on and so forth. So just this formula just gives an insight of the how complex the calculation of pitch angle can be, right? But in modern times we do it algorithmically, and we do it by referencing to the a lot of data stored of the graphs which I showed earlier. But as in this patent it's claimed, in accordance with one embodiment at every refresh cycle of the flight management computer, the phi is calculated, and these formulas are stored in the memory, right? So he's somehow mentioning that in one other patent or something, or it's a part of this patent. I'm not sure about this. So these formulas are stored, and at every and all the time whenever it is asked, the pitch angle is calculated, because these parameters are changing all the time, right? So now we come to the very important diagram, the algorithm which is inside the 737 series airplanes, 737-800 series aircraft, or similar aircrafts, or maybe it's in the future versions, or it's we are just talking about this patent. Maybe they haven't implemented yet inside or not, I don't know. So how it works is that first of all, the pilot enables the IPT function. I will show you in a minute in the interface. It enables, okay, the pilot says give me the initial pitch target angle. So the flight status looks whether the aircraft is on the ground or in flight. If it's on ground, then as we showed in the previous figure, all the takeoff initial takeoff conditions are determined. And then if it's in flight, then the data is got from the avionics bus, and then based on that, right, this is around V2 speed, around at that time when the airplane is taking off, this in flight means, and based on that, continual determination of V2 is happening, or even this is before V2. So here continuous determination of V2 or VS ratio, the same graphs which I showed earlier, is happening all the time. It is continuously looking how to determine the V2, optimum V2 or VS, right? So what he's doing is here, he is referencing a tabular set of data, right? He is referencing a tabular set of data. This means it is like inside the memory a lot of data is stored. Inside the memory a lot of data is stored, and these are the graphs which I showed you earlier, and the computer accesses those graphs and the data. It retrieves it and try to calculate based on those graphs what is the optimum V2 or VS. These are the graphs which I showed you in the earlier part of this tutorial, which was the weight versus V2 or VS ratio based on climb limit and field limit and the optimum pitch angle. So it has a lot of lookup tables out there. He continuously accesses and tries to calculate the optimum V2 or VS ratio, and based on that it calculates the optimum takeoff, optimum pitch angle, right? And then it generates that pitch angle and give it to the display unit and the control unit. And the moment and the moment the altitude is achieved, in this it depends upon the specification, either he is reference to 35 feet or 1500 feet, but let's assume it has a certain reference speed in its mind based on specifications, and the moment that altitude is achieved, it get out, the loop is broken, and it means that the takeoff is done as per pitch angle is concerned, right? If it is not done, then it goes back here, keep on checking the flight status if it's on ground in flight, and keep on optimizing and calculating the pitch angle, right? So this is it's running inside a loop. It's a computer program which is running inside the loop. It's continuously looping around and trying to find the optimum pitch angle, and the moment it finds, it breaks the loop, right? I hope it's clear. So we come to this point again. I come to this diagram here, right? So wait a moment. So yes, so here, right, so here the set of graphs are stored, right? So these graphs which we were talking about, sorry, this tabular data is stored here. This tabular data is stored here. It is accessed by the flight management computer. It is combined with the sensory data and the engine data, and then it determines the initial pitch angle and displays it to the pilot, and the aircraft is configured in that pitch angle, right? So it's all computer algorithm going on here. It's all computer algorithm as we are speaking. It's and so right now we look at how in the display unit is implemented. So this is the artificial horizon which we are seeing, and here is the display of the pitch with respect to the ground, with respect to the aircraft pitch with respect to the ground, and this is the speed, and this is the altitude. I think this is similar. This is for the go around. So here the pitch is then displayed, right? And then this is again the picture of the computer here. Nothing special about it. And here we can see, if we look at this picture, that here the IPT is calculated. So you get the understanding that how the whole flow of calculation of IPT is working, right? It's all algorithmic based. If we look, it's all algorithmic based, and it's pretty interesting, right? As to say, I think I have covered the main heart and soul of this patent. There are, of course, there will be some answer. Not everything is mentioned here because it's a lot of information, but I think you guys have understood what's how this whole system works. So now I will I little bit change the theme of this presentation and just talk about very briefly on my own opinion. I give my own opinion about the 737 MAX crashes which happened mostly after takeoff in Ethiopian, and the Lion Air crash. First of all, I don't know, to be honest, really whether such sort of whether the patent I discussed has something to do with that takeoff mechanism. I don't know about it. I think, this is my personal understanding, that this is highly algorithmic based avionics system. It's relying everything on algorithm. It's relying fully on the loops here, as we saw here, that it's continuously looping around in this thing. So I assume if there is a slight error or mistake here and the calculation is not within the margin, then a different pitch angle can be calculated, right? It can be very nose high altitude, or very nose high pitch, or very low nose pitch. So this point is extremely important, and just imagine, for the sake of imagination, if something goes wrong here, then the pitch can be very different, and something bad might happen. Again, I don't know what I don't know whether such sort of algorithm has a role in 737 MAX crash. I don't know about this, but one thing I can see for certain, that it is highly algorithmic based system out here, which relies on a lot of it relies only on most of sort of software data to reach the correct solution and to find the optimum pitch angle. So this was mostly about this presentation. If you have any questions or you have some comments, please write it in the comment section, or Yeah, and in the end of the day, if you like this video and tutorial and you want to give it a like, so I will appreciate that. And also, if you like to subscribe to my aviation channel, it will be also a nice thing and a gesture from your side. So guys, thank you very much, and I wish you a good day. Thanks.